My name is Gareth McDonnell. For the next 20 minutes or so, I'll be taking you through my journey through the MSc, Building Performance Energy Efficiency and Design. So the research titled Hydrothermal Risk Assessment of External Wall Insulation, or EWI, retrofit to non-traditional wall types in an Irish context using simplified and numerical modelling. The contents of the presentation. First, my background, then an introduction to the topic, research question and objectives, methodology and methods, guidance on hydrothermal risk assessment, failures in external wall insulation retrofit, primary research method hydrothermal simulation, numerical simulation versus Glaser, numerical simulation, a parametric study, and conclusions and recommendations. So my background, I've been a senior architectural technologist, I am a senior architectural technologist with O'Shaughnessy Associates Architects, and I've been working in practice for 25 years. We are a small practice working on projects in sectors such as public works, conservation, residential, education, healthcare, commercial, retail, and I've recently graduated with the MSc Building Performance Energy Efficiency and Design in April. I decided to progress from year 2 to year 3 for a number of reasons. The first was that I'd come so far in the process, I felt it necessary to complete the course and be recognised professionally as having an MSc in Building Performance, Energy Efficiency and Design. I was also intrigued by the research process, how it worked, and wanted to use some of the skills learned throughout the 3 years to investigate an important topic in low energy building design. As the architectural technology profession is not yet recognised on a statutory footing on par with some of our other building professional colleagues, the expertise developed during the 3 years will enable me to specialise in areas which are at the forefront of robust low energy design. Given the retrofit targets under the Climate Action Plan, I felt it necessary to take my education up to master's level to allow me to develop a sustainable business in the area of low energy design. The introduction. The Climate Action Plan published by the government in 2019 introduced a policy of low energy retrofit of 500,000 homes by 2030. The government have recently committed to providing 8 billion of funding to meet these targets. To avoid failure seen in other countries, many challenges will have to be overcome, including moisture risk. EWI is likely to play an important role, especially where a deep retrofit is undertaken. Research from the UK in 2016 indicated that 80% of building failures are moisture related. How are these moisture risks being assessed? Of the 2 available methods for hydrothermal risk assessment referenced in Technical Guidance Document L 2019, a significant preference is indicated for the simplified building modelling, i.e. the Glaser method, whereas numerical simulation is given a minor reference. A survey conducted of NSCI agreement certificate holders for EWI carried out as part of my research indicated that 100% of these use the Glaser method for hydrothermal risk assessment and 29% use numerical simulation on a small selection of projects. So this led me on to my research question. What are the potential hydrothermal moisture risks associated with the retrofit of external wall insulation onto non-traditional wall types in an Irish context? Are those risks being assessed properly? Where and how might they occur? What are the implications? How might these risks be mitigated? The main objective of the research was to undertake a hydrothermal risk assessment of EWI systems on different wall types in different climates using numerical simulation and the Glaser method. A parametric study was conducted using some of the numerical simulation cases, which were then stressed with rainwater and air leakage to assess the implications. Results were compared with Glaser to assess its suitability, and a review of EWI failure and guidance around moisture risk assessment from other countries was conducted to establish the risks and how they are being assessed elsewhere. To increase the accuracy of the simulations, some testing of materials was carried out. So, I've mentioned hydrothermal risk assessment. What is it? Hydrothermal risk assessment is the assessment of the combined effects of heat and moisture on a construction assembly to establish the likelihood of moisture risk occurring and how that risk might be mitigated. It is not a predictor of future events and is dependent on the judgment and skill of the assessor. The 2 currently available methods are simplified building modelling, the Glaser or dew point method, which most of us will be familiar with, and the numerical simulation. The software used in this research for Glaser was BuildSQ 3.4, and numerical simulation was Woofy Pro 6.5. So just I suppose a more detailed description of the hydrothermal simulation methods. Using numerical simulation to assess moisture risks, the WFI software is capable of simulating moisture transport and storage, heat transport and storage, and allows the assemblies to be simulated under stress conditions. Using BuildSQ for the Glaser method to assess the risks of interstitial condensation, vapor diffusion is the only means of moisture transport. The method excludes weather, liquid water, and stressing, and assumes a perfect assembly where these phenomena are considered, where phenomena such as liquid water are considered negligible. The diagram indicates my work. The diagram to the right indicates my workflow through the simulations. It clearly indicates that a lot of the workflow steps are not applicable in the Glaser method. It must be noted that these were desktop simulations undertaken and not reality or predict future events. They're a means of assessing potential risks, and they relied on the data inputs. So my methodology again was hydrothermal risk assessment. So what I've tried to achieve with this diagram was to map the relationships within the overall methodology. The colours relate to the various facets of the research, and the broken lines indicate the linkages between those facets. Green relates to the research question and objectives. The light blue relates to the hydrothermal risk assessment and simulation. Pink relates to the guidance and practice on hydrothermal risk assessment, and the blue relates to results and interpretation. The workflow started with the body of knowledge which provided the basis for the research. That basis influenced the methods, processes, actions, and decisions taken. They in turn provided results which were then interpreted and analysed to answer the research question. So moving on to guidance practice. TGDL 2019 and the NSI agreement certificates for external wall insulation indicate a preference for using the Glaser method, with a minor reference to numerical simulation, as already noted. There is hope. In July 2021, the updated guidance BS 5250/2021 was published. The explicit guidance in the 2016 version of that standard, as indicated in Table G1 here at the top, states that Glaser or no assessment for EWI is necessary. This is now being replaced with a recommendation for hydrothermal risk assessment to be undertaken via a whole building approach, taking into account as-built in-service conditions. Whilst a full reference to numerical simulations is indicated in the 2021 version, the method of hydrothermal risk assessment is left to designer's discretion, a decision which should be based on a whole building approach. However, the outdated 2016 guidance is currently referred to on all NSI certificates for EWI. Research also indicates that 71% of the NSCI agreement certificate holders that responded to the survey were not aware that BS 5250/2021 exists. The Department of Housing and Local Government has clarified that most up-to-date versions of the standards should be used, or referenced in the TGDs should be used. So moving on to external wall insulation failures. Some research was conducted into the literature on failures from other countries, where thousands of properties were affected by poorly installed or poorly designed external wall insulation. Some literature indicated that up to 90% of the EWI failures can be avoided if correct design and assessment is carried out. Poor standard details, workmanship and oversight also contribute to these failures. The failures mostly occur at the interfaces of materials, with window and sills and jambs particularly vulnerable. So I reviewed some of the standard details from the NSCI certs. These are typical NSCI certificate jamb and sill details, and indicate vulnerabilities whereby at the window jamb, where the external render is removed to facilitate the installation of insulation to avoid thermal bridging, the blockwork is left exposed and water can enter the construction through incorrectly or poorly installed single stage seals. On the sill detail, if the soft outer edge, if the sill is compressed at the soft outer edge, the weathering seal between the window frame and sill can be damaged, leaving an open horizontal joint. The stressing conditions for rainwater ingress in the simulations are set at 1% and 2% of the amount of water hitting the surface entering the construction, representing a leak at the jamb and sill respectively. The 1% value is from the widely used ASHRAE standard, and the 2% value was taken from the significant physical study into rainwater ingress in external wall insulation from Sweden. So some suggested improvements to the details were looked at. At the jamb, a suitable weathering tape could be dressed around the reveal from the render onto the render onto the window frame, protecting the blockwork/window interface before the EWI and proprietary seals are applied. At the sill, a more robust high-density insulation product could be installed as a sub-sill to support the outer edge of the sill, and a weatherproof tape membrane could be sealed to the window frame and dressed down over the sub-sill to prevent moisture entering the construction below. So onto the hydrothermal simulation. To increase the accuracy of the simulation, some fully tested materials were procured from an insulation manufacturer, thank you, and some hydrothermal measurements of concrete block were carried out in the CREST lab and TU Dublin Focus Institute. These materials were fed into the WFI database for use in the simulations. Laser analysis and the initial numerical simulations were carried out on 70 cases featuring variations of mineral wool, phenolic foam, EPS, mineral render, acrylic render, and silicone render. These were applied to 3 wall types, in 3 different climate locations. The results from each method were analysed and compared, and also provided a basis case for the selection in the parametric study. For further detailed analysis, 12 cases were selected from a range of low to high risk using 4 parameters equaling 48 cases. 4 stressing parameters were 1% and 2% leaks where the existing window was retained, and 1 and 2% leaks at a position of where a new window might be installed. A constant air change source of Q53.07 was added to the interior surface. The critical monitor positions were placed at the center of the external wall insulation, the face of the existing external render and interior surface. The graphs on the following pages will, the coloured lines on the graphs on the following pages will indicate those monitor positions. Before delving into the results, I wanted to give you an idea of what a low, medium, and high risk look like. This graph indicates an example of a low risk case with mineral wool and mineral render simulated onto wall type 1. The arrows indicate that the critical layers of the assembly, the relative humidity in the assembly has settled in to equilibrium after 3 years. This means that there is a constant pattern of wetting and drying cycles throughout the year where the material or assembly is getting wet and drying at the same rates year after year. These cycles are facilitated by the vapor permeability of the EWI materials, allowing the materials to dry out sufficiently even after being stressed. Each layer of the assembly represented by the colour courses in the graph are below 80% for the most part, or 80% relative humidity for the most part, critical mould, and 95% freeze thaw for the insulation layer. This is a medium risk example that includes wall type 2 with EPS cavity infill, EPS external wall insulation, mineral render base with a silicone finish. The EPS and external cement plaster layers reach equilibrium after 9 years. The relative humidity levels of the plaster layer remain above 80% threshold for 2.5 years. The EPS layer rising above 80% is not significant as mold in this layer is not a risk factor. The graph indicates that the interior surface layers reach dynamic equilibrium after the first 2 years and remain below the 80% mold threshold. This case could be deemed a medium risk due to the risk of mold forming on the existing external render layer in the first number of years when the relative humidity is above 80%. This may not affect the occupants of the building, and there's no air path from this layer to the interior environment. However, the construction build-up could be affected. And a high-risk assembly. The graph indicates wall type 3 with mineral wool and acrylic render. The assembly was simulated for 40 years and dynamic equilibrium was not reached. The relative humidity in the mineral wool is constantly rising and goes above 95% relative humidity freeze thaw threshold after 24 years. A key large-scale long-term study of EWI systems in Germany dating back to the 1960s indicated that systems with mineral render can last up to 35 years and synthetic or acrylic renders can last up to 18 years before needing repair or replacement. Using this research for the basis of assessment, the assembly indicated in the graph is getting wetter as time progresses and the drying capacity is reducing, smaller undulations in the graph. Thermal performance and condition of the materials are likely to degrade prior to the expected service life and need replacement sooner. So the initial numerical simulations were compared versus the glazer. The table indicates a comparison of this. This were 70 cases in total. The table is split into two vertically, with wall type 1 and wall type 3 on the left-hand side and wall type 2 on the right-hand side. As can be seen from the table, all the retrofit cases using glazer passed the assessment. This correlates with the low-risk cases from the numerical simulations on wall type 1 and are similar in wall type 3. However, the risk profiles in wall type 2 are significantly different. It must be noted that no stress conditions were applied at this point. So on to the parametric study. This is where the results become interesting, I hope. The matrix on the right indicates a risk assessment summary of the cases under stress conditions simulated in the parametric study. This analysis identified that 60% of the wall type 1 cases were high risk and 40% were low risk. Of the cases simulated for wall type 2, 67% of the cases were medium risk and 33% were high risk. Dublin was the only location featured in wall type 3. Out of the 8 cases, 50% were high risk and 38% were low risk. The remaining 12% were medium risk. An increased risk only occurred at the new window location in 2 cases, and the rise in stressing from 1 to 2% increases the risk profile in only 2 cases. In all cases studied, those with mineral wool and mineral render are all deemed low risk. Most of the cases with acrylic render are deemed high risk, as only 1 out of 18 cases had the capacity to cope with the moisture ingress stressing. In this slide, I've attempted to provide a starting point for robust guidance around external wall insulation retrofit. Attempt being the operative word. A high-level hygrothermal risk assessment matrix developed using the 1% stressing at the existing window position as a basis. This was carried out by extrapolating the data from the simulations and using the variations in climate to determine the risk profile of the cases in the 3 locations. For example, recognising Belmullet as the most severe climate, if a case is high risk in Dublin or Belfast, it would be high risk in Belmullet. Or conversely, if a case is at low risk in Belmullet, it would be low risk in Dublin and Belfast, etc. The matrix indicates Belmullet, not surprisingly, is the most severe with the highest proportion of high risk cases studied, whereas Belfast and Dublin are quite similar. The effect of the EWI materials on the risk profile is similar to the parametric study, as cases with mineral wool, EPS and mineral render are all low to medium risk, and any cases with acrylic render with either acrylic finish or silicone finish are medium to high risk. Overall, 55% of the cases are high risk, 24% of the cases are low risk, and 21% of the cases are medium risk. Although this is an extrapolation of the data, it is based on the evidence from the simulations informed by the research and indicates a varied risk profile of EWI installations which would not be evident where glazer is used. So, on to the conclusions and recommendations. Numerical simulations have indicated that there is a variation in hygrothermal risk which are not being captured by glazer. The only cases that survived the stressing were those featuring the mineral wool, EPS, mineral render and silicone. These may be the only cases that can be assessed using glazer. If the degradation in condition and thermal performance of the materials are accelerated due to moisture ingress, the likelihood is that they will need to be replaced before the end of their expected service life, needlessly increasing their use and carbon emissions. EWI failures have been evident since the early 90s. These failures occur at junctions and materials. To mitigate further risk of EWI failure, the industry should respond by creating robust details for use on site. The NSEI should not accept substandard details from NSEI agreement certificate holders, and adherence to the BS 5250 2021 going forward is absolutely necessary to mitigate future moisture risks, as the one-size-fits-all glazer method is not appropriate for hygrothermal risk assessment in EWI to guide the recently announced state-funded $8 billion retrofit programme. Thank you for listening.